You will learn how to leverage semantic caching in Azure API management to cache responses from LLM models like OpenAI. Let's start with the question: do you really need cache for LLM models? To answer that question, let's consider these three facts. First fact is that LLM models are expensive to operate because they consume lots of resources. So reducing the number of calls will reduce the cost of your application. Second fact is that users might ask the same question in different forms. The LLM model at the end will give them almost the same answer. Third fact is that LLM models might take too long, few to many seconds, to answer while the user is still waiting for the application to respond. These are three facts and three issues for LLM models that makes it good choice to use LLM caching. Before applying the cache to the LLM models, let's see first how the cache concept works. So typically the user requests will be sent directly to the backend API. But some of these requests are repeated requests. So we take those repeated requests and then we introduce a cache database like, for example, Redis Cache, and we put the request and the answer in that Redis Cache so that the next time the user will run a request that was cached before, the response will be served from the cache instead of the backend API. What that means? This means that the cache here will reduce the latency of these requests because in most of the cases, the cache is generally more performant than the real backend API. Redis Cache is well known for its performance, and in most of the cases, it will outperform your backend API. When we get a faster response, that will enhance the user experience. And then we are reducing the stress on the backend API because the response now will not be served by that backend, but instead it will be served from the cache database. So we can apply the same concept into the LLM models in Azure API management. But there are a few challenges that we should consider. First of all is that now the cached value should be the prompt, which is the user question, and optionally the system prompt, and also the response to that prompt. To save the prompt and its response, almost any database can handle that. But we still have a second constraint, which is how to retrieve the response from the cache. As we said earlier, the user might ask the same question in different ways. So we'll not be comparing text to text right here, but we'll perform this comparison using semantic searching. For that, we need a database that supports the vector searching, and Redis Cache with the feature that is called Redis Search can support that feature. And then we'll need also to use an embedding model in order to transform the user prompt to a vector. And Azure API Management supports this configuration through a policy called Semantic Caching. This policy was introduced as one of the policies that are supported by the GenAI capabilities in Azure API Management. How it works? You decide which user request and response to cache, and then you take that response, you serve it through Azure OpenAI, you take the response, and then you use Azure embedding model. That could be actually Azure OpenAI or any other embedding model in order to create a vector out of that prompt and response, and then you save the prompt and response and vector into the Azure Cache for Redis. This operation actually will be performed by the policy itself. So you just configure the policy with the embedding backend ID, which is the embedding model right here. And then you configure whether you want to ignore or to add the system message. And then that data will be saved into the Azure Cache so that the next time a user will ask a question, the question will be evaluated to check if it already exists within the Redis Cache. How that will happen? So we take the user question, we create a vector for that question by using the embedding model. The embedding model will generate a vector, so we then compare that user vector or that prompt vector to the vectors that already existed into the Redis Cache database. If we find one, then we'll take the response from that object and then we'll return it to the user without invoking the Azure OpenAI model. And if the response is not available right here, so in that case we'll go to invoke the LLM model. So when performing this search on Redis Cache, we can specify here a score threshold, which is the distance between the user vector and the existing vectors right here. Another attribute inside this policy here is the embedding backend auth. So here we are using system assigned managed identity for the API management to authenticate to use the embedding model. Another configuration here is the duration for the cache store. So each time we save an object into the Redis cache, we can specify its TTL, or time to live. This will be expressed in seconds. So if you put here 60 seconds, this means that's 1 minute. After 1 minute, that response or that object will be deleted automatically. Follow me in the next video to see a demonstration for how to enable semantic caching in Azure API management for LLM model like OpenAI. You will learn how to enable semantic caching in Azure API management and OpenAI. For that, we'll be using a policy that will enable us to create an object into the Redis cache that contains the user question and also the response from that question. So then when other users ask us almost the same question, we'll go to check if the question already is available within that Redis cache. If it's available, then we'll take that response from Redis instead of invoking the AI services or the LLM model. So to check for the existing response, we should perform a vector comparison. So we'll compare the vector that is generated by the user to the vectors that exists within the Redis cache, knowing that each cached value will contain a vector. To add security to this architecture, we'll be using managed identity with Azure API management in order to authenticate to the LLM models and also authenticate to the embedding model. That's going to be, in our case, Azure OpenAI embedding model. And in addition to that, our application will use Azure API management subscription key in order to connect to the right API. This lab is available on this GitHub repository, where you can find all the files that we'll be using in order to create the lab and also how to create those resources. So mainly the lab will use Terraform configuration files in order to create the infrastructure. So for that, you will need just to run the commands terraform init and apply, and the following resources will be created for you. To get started, I have cloned this repository into my local machine in VS Code here, and from here I can see all the files from GitHub. So let's start first by analyzing the resources that will be created. So first of all, we'll go create an API management resource. Here I'll create an instance of API management that is using basic v2. And note here how I'm using the AZ API Terraform provider instead of the Azure RM provider, because for the date of recording this video, this does not yet support creating API management with the ST-v2 SQ. And here I enable managed identity. Within the Azure portal, we can see that deployed resource, and that should create this Azure API management. And if we go now to the identity, we should see managed identity, where we have here the identity system assigned is turned on. After that, we create the OpenAI services. So we create an Azure AI service, and then we create a model for GPT-4o, and then we create the embedding model that will be used in order to create the vectors for the user prompts. We can see that resource is available here, Azure AI services, and then if you go to navigate to the Azure AI Foundry portal, and then if you navigate to go to the deployments, you should see the two models, GPT-4o and the text embedding, created right here. Next, we go to import the OpenAI Swagger file. So for that, we use the API management API, where we import that Swagger file, that is a JSON file that contains the definition of the API defined by Azure OpenAI. Then we create an API subscription key that will be used by the user in order to connect. That subscription key is the one available under subscriptions right here, where you can see it, and then you can see its value right here. Then we create an embedding or a backend for the embedding model, where we specify here the endpoint for that embedding model. And from API management, we can see that embedding available right here, and here we can view clearly that URL. If I click right here, then go to properties, we should see the full URL right here. So that will enable API management gateway to communicate with that embedding model. After that, we create the Redis database. So here you can either use Azure Enterprise Redis, but for many Azure subscriptions, especially the one that does not have a credit card attached to it, like the dev test subscriptions, MSDN subscriptions, or trial subscriptions, you cannot create a Redis Enterprise for these subscriptions. And to make it easier for you to follow this demo, I have opted for another solution. Actually, there are two other solutions. Either you deploy a Redis container image into an AKS cluster. If you want to opt for that feature, then you can use this deployment file, this YAML file that will deploy the Redis container, expose the required port numbers, and then expose it through a public service. But that requires you to create an AKS cluster, and that seems a lot for this demonstration. So there are a simpler option, which is to use simply container apps. So with Azure Container Apps, you just create the environment, and then you create the container app, and in this case, that container app will deploy the image coming from Redis/Redis stack. That one contains actually the Redis search feature, which is required to work with LLM models. After that, you expose the required port numbers for the exposed port and the target port for the container, which is in our case 6379. And you mentioned that because this is Redis, it should be using TCP protocol. With container apps, if you want to expose applications through TCP protocol, then we need to attach it or inject it into a virtual network. So for that, we are creating here a virtual network and then a subnet to host the container apps environment. Here we can see that container apps environment and also the container app that is hosting our Redis stack database. Note that here this container will be working as a stateless container, so there is no database attached. This is only for demo purposes. Then the last part here that's still to configure is configuring the policy and also configuring the connection from Azure API management to the Redis cache. Let's see how that works. To connect that API management to Redis, here we have the object API management Redis cache, where we specify our API management, and then we configure or we specify the connection string for the Redis server. In my case, that's this value right here. Note here it's using the default domain or the URL from my container app environment, and then it will attach to it the name of my container app. And then at the end, we put here the port number that will be used by that container, which is, as we have seen here, that same port number 6379. Let's see this in the Azure portal. In API management, you can see a section here called external cache, where you can see here a configuration called default that specifies this ID and also the value, which is a secure value for the connection string. This value actually could be seen if you go back to the API management, and then if you go to named values right here, you can see the value right here. If you click there and then click show value, you can see that's the connection string to connect to my Redis cache hosted in container apps. Great, all is good right now, but we still missed the last configuration, and that is the Azure policy for API management. The policy actually is specified right here, where first you configure the authentication to the Azure AI services through using managed identity. Configure the bearer or the access token that will be get from that identity, and then pass it through to the gateway. After that, in this section, we configure the semantic cache lookup. And here we have the following configuration, like the score threshold, which is the 08, the embedding backend ID, which is the name of the embedding backend API. To authenticate to that embedding model, we'll be using the system assigned identity to the managed to the API management. And then to calculate the vector for prompt, will also include the system message. After that, we have another configuration here for the time to leave, or the TTL, for that cached value. That should be, in this case here, a duration of 60 seconds. We deploy this policy through using Azure API Management API policy, where we configure or where we put the name of that policy XML. So then when we go to the API and select our OpenAPI model, then if we go to inbound processing right here, you can see already some policies have already been configured. And if I click on this icon right here, I can see the full policy applied, and I can see its configuration available right here. That's all for the configuration. Follow me in the next video to go to test this policy through using the API management test interface. Let's now test the semantic caching in Azure API management. Within the API management test console right here, I'll go to provide the deployment ID. So here I'm using the GPT-4o model, and I'll provide the API version as per today. The latest available is 2024-10-21. And then for the headers, I'll go to add an API key, which is the API management API key. That one you can find it within the subscriptions, which is the value available right here. And then next we'll provide a request body, where here we put a JSON file that contains the prompt, which will contain a system message and a user message. So here we are asking the LLM, can you tell me the time please? And then we'll hit save. So the first request will take a little bit longer because this will go directly to the LLM model. The LLM model will response, and here we can see the response coming from the LLM model. Oh sure, because I'm totally your personal clock. And this response right now should be cached into the Redis cache. So the next time we run the same request right here, if I hit send again, then this time the request will run immediately. It will take less time, and we can see that also the response is the same from the previous request. I can try that a third time, fourth time, and it's always the same. So this means we did get this response from the Redis Cache database, because otherwise the LLM model, even if we ask it the same question, will respond with different answers. So remember that our policy is using 60 seconds as a time to leave for the message. So after 60 seconds, if you try, then you should find that here you get another response, because the old response was deleted because it exceeded the 60 seconds, and a new response from the LLM was saved right here. So this was testing inside the Azure API Management Test Console. Follow me in the next video, where we're going to run a test from a Python notebook application. We'll simulate an application that's going to be the Python notebook right here, that will connect to the gateway with AI features in order to test the semantic caching feature in Azure API Management. So to do that, here below you can find the different steps in order to recreate those resources if you want to, using the commands terraform, init, and apply. That will create the following resources that we have seen earlier. And then here starts the lab, where first we need to get some values like the API Management Gateway URL, and then we get the API Management Subscription Key, the Redis Cache URL, and the OpenAI versions. You can see those values displayed right here. We get those values actually because we have exported them through Terraform. So for the API Management Resource Gateway, for example, you can find all of these using the output.tf file that will go to output these values, and then we can use them. So we save it into environment variables or into variables within Python, so then we'll use it later. So we have a Redis instance that is running in Azure Container Apps. We want to make sure that the Redis instance is running. For that, we'll use this sample Redis code, or this Redis library for Python, that will just run a ping against the Redis database, and here tell us true. So this means that the Redis database is up and running, so it's ready to get the requests from the API management. Next, we'll go to make the call using the OpenAI Python SDK. For that, we use here Python code. So we have actually multiple user questions. So here we are asking the same question in different ways. We are asking about the time, and what we'll do here is that we'll run randomly 10 requests, and in each request we'll use a different question, and we should see for all the requests that we get the same response. Let's run that. So in first request we can see the answer right here, which is this one here. Of course, let me just that following, and here for the second request we get the same answer, for the fourth one, and so on, as you can see right here. Great, so this means that the semantic caching is working as expected. Now let's just analyze the performance when using semantic caching, which will enhance the performance of the response. So we analyze here the 10 requests, and we can see for the first request it will take longer because it's invoking directly the LLM model, which take a little bit long, but for the following requests it will take significantly less time.